Hello, everyone. I feel really honored to have a talk here. So my work is called a parallel Primal-Dual sparse method to extreme classification. So one might notice that this funny name PPDsparse. Actually, there's a previous work called PD-Sparse, which we submitted last ICML. There's this whole story behind this. So during the last XML, we're trying to accelerate the training time by like a factor of 100 without hurting the accuracy. And we succeeded in single core version. And this work is about trying to get the same speed up ratio, but also let algorithms parallelizable so that all the industries can utilize their map-reduced infrastructures to get a further speed up on it. So let's first introduce a little bit about the problem setting, and then I'll go into the algorithm details, and then a little bit about the proof sketch, and then I'll show you a little bit about the experimental results. So first of all, I think a lot of presenters have mentioned extreme classification. So this is just a recap of the key points. So we're trying to learn a function of maps between D input features to K output scores, where each output score means is correspond to the confidence score of this sample being that class. And the reason that this is called extreme classification is that we have usually a large number of classes. It could potentially be like 1 million class. And here I want to mention a little bit about the extreme classification is that usually if you count the average number of positive labels per sample, for multi-class problem, you will get 1. And even for multi-label problem, you will get something like empirically less than 10, because each sample can't really be that many classes. And if you do a simple calculation on this, you will find out that the average numbers of positive samples per class is also small, because if you're counting the total number of positive label sample pairs, it's going to be a non-zero value of that matrix. So if you do column or row, it's basically the same thing. So we know that the average number of positive samples per class is much less than the total number of samples n here. That's an empirical assumption that's usually true, and it's also the key point that this algorithm is relying on. And then we want to say that this work only considers linear classifier. So we're trying to train a weight matrix W of dimension D by K, where D is the number of features and K is the number of classes. The challenge is that if you naively train a linear model, it could require number of samples times number of feature dimension times number of classes as the complexity. And for data sets like Wikipedia, you could potentially have all 3 numbers nearly 1 million. So this means this whole training process is somewhat intractable. I personally did some experiment and showed that it takes about 3 months in order to train this on a single core machine. So I want to introduce a little bit about the previous work of all the approaches on the extreme classification. So the first kind of approach is structural approach. So it could mean like low rank assumption or like tree hierarchy assumptions. So this kind of work could have potentially good accuracy and good training time if the data somewhat follows, for example, the low rank assumption. But somehow if the data does not follow this kind of assumptions, your algorithm either have low accuracy or it degrade to things like very slow algorithm. So, and also the thing is that this kind of algorithm somehow is painful to train because you have a large set of parameters. That's my personal pain point about this. Another kind of approach is just a parallelized one versus all model. So a good example is DSMAC. I'm not sure if everyone knows that. It's basically you can parallelize the one versus all model and get speed up linear to the number of cores. And from experiment, we know that it takes days with 100 cores on the largest data set. The issue is that it has good accuracy and parallelizable, but somehow slow, even if you have a good number of cores. And then there's this is the previous work called Primal-Dual sparse. It has good accuracy, it's fast on single core, but it's not parallelizable. And another issue is that in order to store the whole matrix of complexity order dk, usually normal machines need like hundreds of gigabytes in order to store that, and it's not really applicable to most machines. So it still needs days of largest data set. And this paper is called Parallel PD-Sparse. It tries to combine all the previous work. So it has good accuracy and it's fast, and we guarantee that it can be further parallelized. So it achieves less than 30 minutes training time without hurting accuracy and have good, with 100 cores. Yeah, this is basically what we have done. And then I want to talk into details why this algorithm, how this algorithm is constructed. So first, this is the definition of class-wise separable hinge loss, which is basically means that the loss is this maximization, which basically means we want to push the positive label to the right side. If it's not further, if it's inside margin, there's a loss, and similar situation for the negative samples. And minimizing this separable loss is equivalent to the one versus all model. So I'm not going to introduce this in more details. And to further enforce sparsity, we add L1 penalty on weight matrix. And we also something called bias per class, which basically means we add constant feature 1 to each sample. So I'm not going to derive this, but the dual problem of this L2, L1 regularized problem have this kind of form. And the thing we need to notice that is here we have primal variable W, and we have dual variable alpha. And there's an equation that W equals X, which is the sample matrix, times dual variable, and applying the L1 proximal operator. So we want to take a closer look at this diagram. So this is the whole procedure of this algorithm, and it also explains why we can achieve good speed on this. So first of all, suppose you have all the primal variable and dual variable set to 0. And the first thing you need to do is you maintain an active set, which is correspond with respect to each class. So the whole process is separable with respect to each class. And you want to find out the positive samples for each class, which is defined by AK here. So the first procedure is to search AK. And here we want to find out the coordinates that has the largest gradient. And suppose if you want to exactly compute the gradient, it could potentially be really expensive because this thing is not guaranteed to be sparse. So first approximation is that you need to do random sparsification on the weight vector WK. So the random sparsification could be implemented as uniform sampling, but in practice, we use L1 sampling. So if we have L1 samplings on WK, the situation is that you can still get good accuracy, and here's the reason. Because in this search procedure, you only need to find the largest gradient, the coordinates that has the largest gradient. If the largest gradient and the second largest gradient has a big gap, you don't really need to compute the gradient exactly. You only need approximately estimate which one is the largest. And the next thing is that even if you pick the second largest gradient, it doesn't really hurt that much in the convergence rate. That's like a practical sense. So in this sense, we actually have a good tolerance on the search procedure. And suppose we have the search procedure because we are searching greedily on the active set. The active set is potentially really small. And then we only need to update dual variable. We only need to update dual variable with respect to a small active set. And that's why this update procedure is fast. And then after we get like the delta alpha, which is the deviation of the dual variable, we maintain this equation, which is the constraint here. And by maintaining this, and because the delta alpha is somewhat sparse, and that sparse comes from AK. So if that is sparse, we can guarantee that this maintained procedure is also fast. And then we are looping back to the next iteration. So this is the whole procedure of this algorithm. And a simple analysis shows that the complexity per iteration is with respect to the number of non-zero elements of WK and alpha K. So in the next few slides, I'll try to give a proof sketch about how these two numbers are bounded. And I want to talk a little bit about why this thing is parallelizable. And I think the reason is pretty naive, because that's exactly the reason why one versus all laws can be parallelized. What you need to do is just separate. You just train weight vector with respect to each class separately, and parallelize them. Do some load balancing. You can get basically linear speed up, even with 1,000 cores. And the next thing is that it addresses the space issue because you only need to store the weight vector, not the weight matrix. So your complexity is D, not DK here. So I want to give a little bit proof sketch. So here, the first thing we are relying on is that the number of positive samples per class is small. And we want to bound everything using this in terms of this NP. So the first step is we can bound the L1 norm of primal and dual variables. And the way to bound them is basically you choose like a special value, and because your loss is minimizing the whole thing, and L1 loss is like one term of it. So you can choose a special value that zeros the other terms, and in order to, you should be able to bound like L1 norm of each. I'm not going into details for that. And then if you have like L1 norm of primal and dual variables bounded, you can further bound the number of non-zeros of these two variables in terms of the L1 norm. And this is because, so the first part is basically because the nature of L1 sampling, and this one is somewhat similar. And I want to show a little bit about the results. So the blue numbers are the training time of PPDsparse. And you can see that especially for wiki LSHTC 225K, we only need something like 6 minutes. And things like all the previous works takes days in order to train it. And we basically have the same accuracies or higher. This is for multi-label classification. And for multi-class, basically the same thing happens. It's not that exaggerated, but still the similar thing. Okay, so that's all I want to talk about. How I'm doing with the time.
Well, you have more time, but
okay.
let's thank the speaker.